This is for Year 12 Specialist. It comes out of Chapter 12. It's the notes about 12C vector calculus. In vector calculus, we're going to use the derivative of vector functions. So if I have the position vector r of t, its first derivative, so d dt of r of t, so the derivative of the position with respect to t, we write as being r dot of t, and it's going to equal the derivative of the x component in the I plus the derivative of the y component in the j with respect to t, and it's also equal to the velocity vector. The second derivative of the position will be the second derivative of x of t with respect to t in the I plus the second derivative of y of t with respect to t in the j, and that's going to be the acceleration vector. So the derivative of displacement is velocity, the derivative of velocity is acceleration. If the derivative is equal to 0, then it's a constant vector. Again, we can take the k out as a common factor. We can write them separately as two separate derivatives, and I can use a product rule when I have two vectors that are being multiplied. The same works with anti-differentiation. So if you anti-differentiate the acceleration vector with respect to 2t, you will get the velocity vector plus some constant c. Remember that constant c will have an I component and a j component that each need to be worked out separately. So remember, c has some I component plus some j component plus some k component if there were three components to the position vector in the I, in the j, and in the k. Okay, so what does that look like? 12C, sketch the graphs of each of the following. Find the initial position, the initial velocity, the initial acceleration. Okay, so TO is 0, so that's where I start counting. So to do these answers first, R of 0 is going to be e to the 0 in the I plus e to the minus 0 in the j, which is 1I plus 1j. Therefore, R of T0 equals I plus j. That's the first answer. R dot of t is going to be the first derivative, therefore e to the t in the I minus e to the t in the j, so R dot of TO is going to be at time 0, so I minus j. And R dot dot of t is going to be e to the t in the I plus, so that's minus t, isn't it? So I need to draw it. So I'd like to put it into Cartesian form. So I'm going to make x equal to e to the t and y equals e to the minus t. And I could rearrange that to say y equals 1 on e to the t, and since e to the t is x, therefore y equals 1 on x. So that's my Cartesian equation. I know from my answer before that it initially starts at 1, 1. So it's going to be there, that's my starting position. I know that the range of x of t is the domain of x. The range of x will be 1 to infinity. Therefore, I'm going to start at 1 and go to infinity. So this should be, it's 1 on x, so it's a hyperbola. And that's at 1, 1. And the range of e to the minus t would be 1 to 0, so 0 to 1, and it's inclusive of the 0, so that makes inclusive of the 1, but not of the 0. So therefore, that's going to be my graph. So I know that r of 0, it starts at 1. R of 1 is going to be 1 in the I plus 1 in the j, so therefore I plus j. R dash of 1 would be the derivative of this, which is 1 in the I plus 2t in the j. Therefore, r dot 1 will be I plus 2j. And if I'm looking at r dot dot of t, the second derivative will be 0 in the I plus 2 in the j. Therefore, r dot dot of 1 is going to equal 2 in the j. So that's the acceleration initially, that's the velocity initially, and that's the position initially, which is what these three questions up here are. But of course, I start at t equals 1 because that's what I've been told. Now to draw it. Okay, so I've got x equals t and y equals t squared. Therefore, y equals x squared is going to be my Cartesian as being the graph of this position vector where it starts